This is a fun game of trying to figure out where you guys are. Carson, that looks like someplace in ERC based on the lighting. I guess it's Manti Center now. Elijah, I have no idea.
Actually, I think it's the top of Baldwin. Yeah, I'm in Baldwin.
Oh, okay. I'm,
Yeah,
I'm glad you know where you are.
yeah. I had to look outside. I get confused because they're all like the same building.
Yeah, there. I'm gonna have to update my emoji, my avatar as my hair gets grayer. It's gonna need some frosting on that. That was the one that I generated in spring of 2020 when we went on lockdown. I would put a Bitmoji on the title slide every day to kind of make it a little less stiff. I don't know if that worked or not. I answered 5 questions, and that's what my phone thought I looked like. I think maybe my wife picked that out for me or something. Maybe that's what she wants me to look like. Does it look like Ryan Reynolds? Because that would make sense. Hmm. All right, we're one day shy of November. That's sobering. All right, let's get started. How many are we? I got me plus 4. Should be me plus 7. All right. Yeah, this class is easy to get behind, easy to put it off because everything's recorded and you can yeah. I had a class like that back in like 97, 98. It was at Georgia Tech and it was almost before the internet, not quite before the internet, but almost. And for whatever reason, this class was taught in a recording studio, like a place where you would you know broadcast the news from or whatever, and they would record it on VHS tapes at the time, which was cutting edge then. And then they would put the tapes in the library. And I think what they were doing is they were sending those out to the branch campuses of Georgia Tech as well, because we had a branch campus in Savannah and another one down in I forget what the name of the town is. Down in this on the southern border of Georgia with Florida. And I think that they were offering it as a remote class at that time. And the only way to really do that was to basically FedEx the videotapes down there and let people watch it. Anyways, as you might imagine, I got behind in the class because I knew I could always catch up on the recordings. And so, like the week before finals, I spent like 15 hours in the library watching VHS tapes on fracture mechanics, and that was 15 of the best hours of my life, I'll tell you. All right, let me get started then. Right, so today is Tuesday, October 31st, Halloween. Here's my schedule for the week. I didn't have any visitors in office hours this morning. I hope I didn't post my office hours for this class until after office hours, so I hope nobody missed that. But you guys all know where to find me by now. So I'll have office hours again tomorrow, and those are going to be from 1 to 2:30. But Dr. Elzarka just called a meeting of our faculty, so that's going to conflict. But I'll try and do both at the same time. I think I can do the meeting online, and basically kill two birds at this with one stone. All right, here's a list of our homework due dates. So we have the 2D analysis of the Tower of Terror set up, and that's due this coming Friday. I had a message from Carson on Thursday or Friday of last week asking about some details about what was required for that assignment. And that email from Carson prompted me to post an update to the assignment. I don't know if you guys get push notifications from Canvas when I do that. So let me take a minute and show you what I did then. There we go, Canvas. I'll probably get it's going to send me a push. Oh, thank you. And it's this class. And if we go to assignments, there we go. First order 2D analysis of the Tower of Terror. So I actually posted an Excel template that you can use for post-processing your data. So now let me find that template. I'll actually use the version that's on my computer. That'd be there under homework number 7. There it is. And so with this worksheet really, then what it's set up so that if you do your analysis and you name your members the way that I wanted you to, then all you have to do is post the data in the appropriate sheets here at the bottom. Let me see, here we go, moment frame output. So you can post your data into this sheet from the moment frames. And let's see, the next one is probably concentrically braced frame output, CBF output. So if you name your joints and your members the same way and output the data the right way, then you can paste your output into these 2 sheets here, and then that will basically sort all the information for you. And so I've got results due to dead load, curtain wall, snow, live, and wind in the X direction. And then I have the load combinations that I want you to consider. And then the envelope, and the envelope is presented 2 different ways. First, it's in kips and feet units, and then kip and inch units. And it's convenient to have both of them. And then some joint output that calculates the drift ratios and things like that. And so as you're working through your assignment, it might be worth taking a few extra minutes to number your nodes and your members the same way that I did, so that you can save some time on the back end with your post-processing. You can always change the this information here, but if it's one of those cases where the equations that are in these cells are a bit involved unless you're the one actually writing them, right? It's like me trying to tear apart one of Joe's spreadsheets that he's using to post-process some of the data we're working on. If you're the person writing the equation, it makes a lot of sense to you, but if you're trying to make sense of somebody else's work, it's a little bit confusing. But the way that's written anyways, if you change the load combination name up here, that should work for you. If you go over here and change the name of the member or the output station, that should work for you as well. But you guys should know how to do this, but I recognize it's not easy. My intent wasn't to make it more complicated. My intent was to save you some time, and I hope that that's the way that works out. Carson, did you get that far? Did it work for you?
Yeah, when I asked you the question, I was already basically done. So I just
Okay.
continued to add my screenshots in there instead of using this.
Okay.
Excel
Well, that'll
sheet.
teach you to work ahead then, right?
Yeah.
All right. Okay. Well, that being said, what I wanted to do today is pick up on where we left off last time with our continuum elements, and then I'm going to go back to SAP 2000 and put some shell elements in that model and show you how to basically put in the gravity loads. And then if there's any time left over, we might launch ETABS and start working in there as well. So looking ahead at our schedule, my goal for Thursday is to talk about matrix analysis of frames. So that'll be our last matrix conversation. And I wanted to get that in before our exam. One of the exam questions that I like to ask is, calculate equivalent end actions. And if we do that for a frame, that's a little bit more interesting than doing it just for a beam. And so I wanted to get that in before the week of the 13th. Remember, next week, when we look at the 7th, that's a reading day for us, so we won't meet that day. And then we basically, after this week, we have one more class before our take-home exam. So that's on the 9th, and I plan to answer some questions you might have then, and then cover some ETABS material. And then we have our exam, and then basically 2 or 3 more classes after that, and we're done. So month of November goes fast. All right, so let's see. We were working in the this presentation here. Okay, we were working on continuum elements in SAP 2000. We talked about the differences between plane stress and plane strain elements. The idea that these elements come in either 3-node triangles or 4-node quadrilaterals. There's different variations of those, so you can actually have a 6-node triangle or an 8-node quadrilateral or even a 9-node quadrilateral that have different types of shape functions that are built in, different formulations that are buried behind them. And then we can deal with other types of plane elements that are shell elements. And instead of handling in-plane stress or strain, they typically handle out-of-plane stress or strain. And then when you combine, that's actually a plate element. When you combine a plate element and a plane stress element, you get a membrane element more or less, and that has bending and in-plane actions in it. So the shell elements that we work with look like this. This particular formulation is showing 5 degrees of freedom at every node, 3 translational and 2 rotational. And the 6th one that's missing from this is a drilling degree of freedom. And that can be included as well, depending on which software packages you're working with. And so here we show that drilling degree of freedom as well. I took the shot out of the SAP 2000 manual. I printed it out and I sketched on top of it in pencil, and I scanned it back in, and that's the image quality that I'm dealing with here. Yeah, so we're going to use these shell elements because they do a good job of modeling floor slabs, bridge decks, structural walls, and things like that. And if you go on and take like a modeling class like 7012 or 7013, you might use brick elements and things like that, but we're not going to get into that in this class. So really this idea of a continuum element is really in place to model things like this bridge deck or to model floor slabs in buildings. All right, so we had talked about the idea that there has to be some transitioning in the meshing in order for this to work. The only place where these continuum elements are actually connected to each other is where they have common nodes. And so you need to have a transition mesh between the 2 different regions of the model in order to have continuity of action. So if we were to go in and push down on the top of this, then what you end up with is overlapping between these 2, because this shell element up here isn't connected to the shell element down here, except at that one node. So you have a node here that's on the top, a node here on the bottom, and those aren't connected to each other. And so we can use a transition mesh like that, or we can use an edge constraint like this. And those edge constraints are handy because they allow us to just define a set of joint constraints that accommodate the transition mesh. The transition mesh is a little bit more costly in terms of time because you have to go through and do that manually. You can't always get Abacus or SAP or ANSYS or whatever to get that transition mesh for you automatically. All right. Now, here's an interaction between 2 different types of elements. So to the left of point A, we have a continuum mesh, plane stress, plane strain elements, or maybe shell elements. To the right of point A are 2 beam elements, and then those are linear elements. And so one issue that comes up here is that when you want to, say, look at a beam that's embedded in concrete, you might model it like this. But if we look at the degrees of freedom that are associated with the continuum mesh, we would have translational degrees of freedom at each one of these nodes like this, right? But when we look at the degrees of freedom that are associated with the beam element would have translational and rotational degrees of freedom. And so we do that here. So here's the beam degrees of freedom. So the problem is that there's no rotational degree of freedom corresponding to the continuum elements at point A. And so if you build this model and then come in and put some external load on the beam out here, then all that's going to happen is that beam is going to be able to undergo a rigid body rotation because there's no rotational degree of freedom at node A corresponding to those continuum elements. So in order to properly model this, what you're going to have to do is extend this beam back into the continuum mesh so that when you go and put your load out there at the tip of the beam, then what happens is you actually develop a vertical force at A and a vertical force at C. When multiplied by the distance between them, that would be equal to the moment that's generated by that force at the end of the beam. So there's no rotational degrees of freedom in that continuum mesh, but the two translational degrees of freedom acting over some moment arm gives you the same effect that you would be looking at. Now, an alternative to that would be to come in and use a joint constraint. Maybe you could use like a beam constraint or a plate constraint and constrain those three elements, and then they would have to move as a straight line. And then what you could do is you could use the translational degrees of freedom at those two nodes to generate the moment that you would use to offset the moment at the base of that beam. So that's kind of an abstract idea. Probably one of those things where it won't really clue on you until you actually are faced with that situation. But if you come up against that kind of a situation, bear in mind that's an issue that you have to work around with these. So when we go and use these continuum elements in SAP 2000, we're going to use most often, we're going to use area elements. So the beams and the columns and that we've been drawing, those are frame objects or linear objects. And what we're going to do now are use area objects. And like we take a linear object and we automatically mesh it into a number of frame elements, we're going to take an area object and then we're going to automatically mesh it into a bunch of shell elements. So an area object can be larger, and then you can set the automatic meshing so that it's meshed into a number of smaller shell elements. And so the area objects are on the toolbar and they look like that. So you have the first one is for an irregular area object, and the second one is for a rectangular area object. And so occasionally you end up with an irregular shape depending on the particular geometry of the structure you're modeling. You also have to define the area sections, much like when we define a frame object, we have to tell it whether it's a W36 by 150, or maybe it's a rectangular concrete beam, 18 inches by 12 inches. You have to do the same thing for the shells as well. And so you go into the define menu, section properties, you go to area sections, and then it gives you a window that looks like this. And so you can define the area as either a shell, a plane, or an axisymmetric solid. And so that's what those three options are for. And we talked about these different types of elements that exist under the idea of continuum elements. And we're almost always going to use a shell element when we do our modeling. In the past, in this class, I played around with modeling a dam cross-section. That's different than a dam cross-section. A dam cross-section with plane elements, but it's kind of a right turn from what we are doing with buildings and bridges, and so it doesn't really fit in really well with the cadence of the class. And then we always run out of time anyway, so I haven't done that in the last couple of years. Another option would be you could actually model a wide flange beam using shell elements. You use a series of shells for the top flange, a series of shells for the web, then another series of shells for the bottom flange, and you can get a high resolution model of a beam using those shell elements. And there are some applications where that's preferable, but that's using SAP basically to about its usefulness. That's pushing SAP to its limits with respect to doing continuum modeling. And if you're going to do that type of work, you're probably better served going into something like Abacus or ANSYS instead. Excuse me. All right, so second step is to define the area sections. Once we go in and look at the shells, then we have to go in and define more details. So we have different types of shell elements, a thin shell or a thick shell. We can model it as a plate that's either thin or thick. They're missing a hyphen here. I got to fix that. There's also a membrane option that's available, or a layered nonlinear shell. And that layered nonlinear shell is something that I don't play with very often, but there's a watch and learn on CSI's webpage. If you're going to do any modeling of concrete buildings and you want to have a shear wall included in that model, then you can do a layered shell element formulation for that. And there's a rather sophisticated way of handling the rebar that's in that shear wall. So I'd encourage you to go and watch that watch and learn if you're interested in that sort of thing. So there's two different types of thicknesses that are here. There's membrane thickness and the bending thickness. And so when we're defining a floor slab, the floor slab has one thickness, right? It's 8 inches, 12 inches, 6 inches, whatever. But there's two different thicknesses that are given when we look at the shell data, because one of them corresponds to in-plane behavior and the other corresponds to bending behavior. And so if you put a 0 in for the membrane, then that basically removes the diaphragm action that you would get out of the floor plate in a building. But you could enter a non-zero or a positive value for the bending thickness, and then it would carry the transverse loads to the members that are supporting the shell elements. Or you could do vice versa. You could put in a positive number for the membrane thickness and a 0 value for the bending thickness, and that would give you the diaphragm action, but not the transverse bending action. So there's some options that are available to you there. You can use different types of materials. The default is probably concrete. And then you have the same options that you had before with the property modifiers and the stiffness modifiers and those sorts of things. Okay, the next is to assign the area section to the area objects. So you define where you want the shells to be, you define what you want the shells to be, and then you assign the shell section definition to the area object definition. That's rather intuitive after you've been working with SAP and you understand that you have to assign a section to all the frame objects as well. Then the next step is important. It's not strictly required, but almost every case you would want to do something with automatic meshing associated with the area objects. So when we go and look at a framing system for a building, the beams might be spaced at 12 feet, and you certainly wouldn't want to have a shell element that has dimensions of 12 feet by 32 feet. One element that's that large isn't going to give you the analytical results that you're looking for. What you're going to want to do is break that up into a number of smaller elements, and in order to do that and do it conveniently, you'll want to use the automatic meshing. And so you set that much like you do automatic meshing for a frame element. You go to the assign menu, you go to the area, and then you go to automatic area mesh. Now, when you look at the dialog box that comes up, it's very involved. And there's a whole 2, 3, 4 page handout that I have that I'll give you on this. But I should have posted it before class, but I forgot about it. But in almost every case, if you select these options here, that gives you usually the results that you want. I use the cookie cut based on straight line objects that are in the meshing groups, and I extend all the straight line objects to the area edges. And so what that does, if you window over an area object over the floor framing at a given level in a building, what it'll do is it'll automatically mesh that area object so that the edges of the resulting elements line up with the beams that are in that floor slab. And so that's usually what you want. And then I also have a sub mesh option over here, rather arbitrarily. In this case, I've selected that I want elements that are no larger than 12 inches by 12 inches. And so that's not a bad number. If I have floor beam spaced at 12 feet, like I do in the Tower of Terror, then that's going to give me 12 shell elements between each floor beam. That's not a lot, but it's not too few either. If we were looking for behavior of the deck itself, we might want a higher resolution mesh. But since we're not really looking for the behavior of the deck, instead we're looking for the loads that are in the steel members instead, then using a mesh that is rather coarse is satisfactory for that particular objective. Right, so there's the automatic meshing that I use. Yeah, I'll post that. I forgot to post it before class. And so the idea is if we go in and window over a a series of members like this, then we can automatically mesh it and get it to pop up with the straight line objects. Now, there's a difference between the model that we use for design and the model that is used for analysis. And so if you want to see what type of automatic meshing is going to happen, then you go to your display options dialog box and show the analysis model, and then it'll go through the automatic meshing. Right. Yeah, and there's that. All right, now let me skip over this for now. The plane stress and the plane strain elements, I don't think we need to cover those. Yeah, here's one. I did do a model of a shear wall with these plane stress, plane strain elements. I guess I'll cover them just to be complete, but I'll cover them quickly. Okay, so the plane stress, plane strain elements, they have a use when you're modeling things like walls, or maybe you want to do a model of a beam and you want to look at the stresses in the beam. And in this case, you could actually look at stresses that are based on the finite element formulation instead of stresses that are based on Bernoulli bending or Euler bending instead. And so there's an option for including incompatible modes. And when you look at a beam that's made up out of these plane stress, plane strain elements, you end up with a propensity to have shear locking involved with them. And that's where the incompatible modes come into play. Plane stress and plane strain elements have loading that can consist of self-weight or gravity, surface pressures, pore pressures, or temperature. And you can also put point loads at the joints that are within the model. The output is based on 2x2 numerical integration, Gauss quadrature that I mentioned last time, and it gives you stresses in the local element coordinate systems. So you get in-plane stresses in the 1,1 direction or the 2,2 direction. Those are sigma values. These are normal stresses. So that would be sigma 1,1 or sigma 2,2. You also get a shear stress that would be tau 1,2. And they use S for all three of them. So you have to be familiar with the notation. You also get an out of plane stress in some cases, depending on whether you're using plane stress or plane strain. And then you can also output the maximum and the minimum stresses as well, or the maximum shear stress too. And these are based on, so here's the output definition. So sigma 1,1, sigma 2,2, tau 1,2, S min, S max, and then the maximum shear stress. And those values are based on a Moore's circle analysis of the state of stress that's in each one of the elements. And so you might have a value where this is sigma 1,1, tau 1,2. This might be sigma 2,2, tau 2,1. And then the maximum stress is here, the minimum stress is there, and then the maximum shear stress would be up there. All right, here's the shell element formulation. You can have a 3 or a 4 node formulation. The 4 node element does not have to be planar. You could have the 4 nodes out of the same plane, but it shouldn't be too far out of that plane in order to give good performance for that. Each element can be loaded by gravity or uniform loads in any direction, surface pressure, or strain or temperature change. There's also a uniform to frame option that's available for the shell elements that's very useful. In a lot of cases, we don't necessarily need the shell elements in the model to try and capture some behavior. In a lot of cases, we just want the shell elements so we can put the gravity loads on there. So we can put the dead load from the floor, or the snow load, or the live load from the floor on there. And in that case, a uniform to frame loading option is very, very useful to us. The default axis, the default orientation is confusing. I won't read this to you. I'll let you figure that out on your own. But one of the things you're going to want to do when you define these shell elements is go and look at the orientation of the local axes. The 1 and the 2 axes are usually in plane. The 3 axis is perpendicular to the plane of the shell element. And when you define the way the loads are distributed, you have to know whether the 1 axis is perpendicular to or parallel to the members that are supporting the shells. And if you get it wrong, then the behavior that you're expecting might be different than what you get. Excuse me. All right. So if you want to show the local axes, I think we talked about this in the context of frame objects, but in area objects, you can go to the display options. show miscellaneous assignments, and then go to the area objects, and you can show the local axes. And so it shows a series of red, white, and blue axes. And so like this, in this case here, I've got a wall that I modeled. So red, white, and blue corresponds to 1, 2, and 3. They can't show a white, so it's red, green, and blue instead. So the this would be the local 1 axis here. This would be the local 2 axis, and then the 3 axis is coming out of plane. Okay, these shell elements are based on 4-point numerical integration, 2x2 Gauss integration. There's an approximate error in the elements that can be estimated by comparing the results. You might have 2 shell elements that are up against each other like this with common nodes, and you can compare the forces you get from this element at this node to the forces you get for this element at that node. So same node, but different element, you get different forces. And if you want to know how much error is in your model, then you figure out how much difference there is between the forces you get from those 2 different elements. And if that difference is quote unquote large, then you should refine your model and use a more refined mesh. And if it's small, then your model is okay. So thin formulation neglects the out of plane shear deformations. That should be plane. It's funny I didn't catch that in the years past. While the thick formulation includes it. Whether or not that's important is up to you. It's probably not important for most of the work that we do. Most buildings have a rather thin floor slab, something in the order of 6 or 8 inches. Maybe if you get into a bridge deck where you have like a 12-inch or 16-inch thick bridge deck, that would be very thick even by today's standards. Then maybe that would be a case to include it. But probably in most cases, we can ignore that. Then you have the homogeneous versus the layered. And this is a reference to that watch and learn that I mentioned earlier. You can use a layered shell element formulation to model shear walls. All right, so what I want to do at this point then is shift gears, change computers, and go over to SAP 2000. So that'll take just a minute. You can go over here. Share that window. There we go. And there is the model that I have of the Tower of Terror. All right. So this is basically where we left off last time. So I'm looking at the first story of framing. So that's floor 2 right there. Let me actually go over here in the window on the right. And what I'm going to do is take a look at the second floor framing plan in a 2-dimensional view. So I'm going to go over here on the right. I'm going to go to view, set a 2D view. I want to look at the XY plane at Z equals, I could type in 12.5 feet, or I could just click there. That's the second floor framing. I hit apply, and then there's the second floor framing for me. All right, so I've got to do 2 things when I look at the wrong camera. I got to do 2 things. I've got to define the geometry of the shells. I've got to define the section of the shells. I'm going to define the section first, because then I can assign that section to the area objects when I draw them. So let me go to define areas. I'll say I want a new shell element. Let's call this floor slab. And so I'm going to use a thin shell element formulation. Let me go ahead and use a membrane thickness of 0.5 feet, a bending thickness of 0.5 feet, and I'll just keep this material that I have here. Using concrete, normal weight concrete is satisfactory. And I think everything else will be fine from there. Okay, hit OK. Now what I can do is I'm going to draw one area object that represents the entire floor at that level. So I go in like this. I'm going to draw it from upper right to upper left to lower right. And you can see that area object there. It's outlined in red. And then I'll hit escape to exit out of that. Now, if you want to see that area object a little bit better, what you can do is go in here and go to either fill objects. And so now it fills in that area object with red, so you can see it there. or you can go in here and shrink that object so that you can see, it's actually shrunk down from its edges. And so it's hard to see those area objects sometimes. You can also go in here under areas. You can put the labels in there as well, which sometimes helps. So that's area object number 1. We can put the sections in there. So that's floor slab. Or we can go over here and I can draw the local axes, and that will be helpful. So let me not fill that object. And so now the one direction is parallel to the joists that are in there. Now, let's see. I want to check one thing. I'm going to go up here and go to the documentation. And let me go to search instead. There we go. So the uniform to frame option works in one of 2 different ways. I wish I could get rid of that highlighting. You can have it set up so that the area objects behave as a one-way slab or as a two-way slab. And I'm looking up to remind myself, when I put it in one-way mode, does the load distribute in the one direction or in the 2 direction? And I can't remember which that is. So select the distribution for the load. When the one-way option is selected, the load is distributed in the axis 1 direction. When the two-way option is selected, the load is distributed along both the 2 and the 1-way. So what that means is when I define one-way slab action, it's going to carry the load in the 1 direction to the supporting members. So I want the 1 direction, the red arrow here, to be perpendicular to the floor beams. So I can do one of 2 things. I can either delete that area object and redraw it, or I could come in and I can change the local axes. So let me go and do the latter. I can go in here to assign area and then go local axes, and I can define an angle of 90 degrees. And when I do that, then you see now the one axis of that area object is going perpendicular to the floor beams. All right, I'm going to do one more thing. I'm going to select all of the members that are in that floor slab. And then I'm going to go into the assign menu, go to area objects, and then automatic area mesh. I'm going to go in here. I'm going to auto mesh using the cookie cutter based on the straight line objects that are in the meshing group. I'm going to extend all those lines to the area edges, and then I'm going to go in and select 1 foot for the size of my elements. All right, so I hit OK. It gives me a little indication here that it's doing automatic meshing. And now if I want to see what the actual elements look like over here in the right, what I can do is go to my general options and show the analysis model. Okay, the analysis model hasn't been generated yet. It's asking me if I want it to do that. It asks because for larger models, it takes a non-trivial amount of time. And even for this model, it takes a little bit of time. So it took that one area object and broke it down into all of those shell elements. And so all of those shell elements look like that. All right, that's kind of strange. I wonder why it broke it down into a different number of elements on the top side of that than on the bottom side. That's unexpected. Let me go in and do something else here. Let me break that down into a smaller number of elements. Let me go here to assign area, automatic mesh, and instead of having 1 foot by 1 foot, let me specify 4 foot by 4 foot. Okay. Oops, that's not what I wanted. View, 2D view. Where did it go? Hit apply. Okay, there we go. Okay, let me see. Go in here for look at what it has for automatic meshing. Yeah, submesh is 1, so it didn't take that last edit. So let me go in here again. select my area object, go to assign, area object, area automatic mesh, and hit apply. There we go. Now it killed the analysis model. Let me go ahead and hit apply again. There we go. And so now it has larger elements. So one of the things that's important is, let me go ahead and do that same thing over here. One of the things that's important is if you actually want the shell elements to be connected to the beams that are supporting them, and you do, then you have to have the beams set up so that the beams automatically mesh at every location where there's a node. And so there's going to be a node at every corner of these shell elements. And so these beams all have to be set up so that they automatically mesh to connect at those nodes. If you don't do that, then you'll get behavior that's unexpected. So what I'm going to do over here on the left view is I'm going to come in and I'm going to say that I want the areas to be not in the view. So there's area objects there, but they're just not shown. And then I'm going to right click on that supporting beam, and I'm going to go in and look at the automatic meshing that's associated with that beam. The properties, materials, local axes. Huh. Wonder why it didn't give me automatic meshing. Did I miss it? Local axes. So maybe I didn't define that. Let me go. Oops, I did the same damn thing again. Go to assign, frame, automatic meshing, at intermediate joints. Yeah, okay, it's already set. All right, well, let me do this. I'm going to go ahead and load that area object. So let's go ahead over here. I'll select that area object. Note when I click on this, I can't select one of these elements. I can only select the area object that's submeshed into those elements. I can go up here now to assign, go to area loads, and now I can put a uniform load on that. And so I can put, say, a dead load on, and I can type in 65 pounds per square foot, and that converts to 0.065 kips per foot. Let me hit apply. And then let's go ahead and run the model once and see what kind of results we get. Okay, note that the model takes a little bit longer to run now because it has a lot more degrees of freedom in it than it did before. And I'm getting an error. Yeah, let's ignore that for now. I shouldn't ignore that, but let's ignore that for now. What I want to do is go in over here on the left and show them bending moment diagrams due to dead load. And that dead load moment diagrams that are shown there are coming in from the shell element loading. So let's go here to display. Options, go to moment diagrams on the tension side. Now we're getting a dead load moment diagram for that beam. So I can go in and right click on that just like we did before. And bring up my beam object. And so you can see the bending moment diagram that is in there. So I have a maximum moment in that beam of 38 kip feet. It's not exactly what you would get from WL squared over 8, but it's not too far off. Now we have a little bit of an aberration here at the end, and that's because the shell elements that we put in are continuous over the girder, right? The beam is pinned at the girder end, but the shell elements are not. And so if we want to, we could be a little bit more sophisticated in defining our mesh, or if we go in and define a zero membrane thickness, then that will take away all of the, a zero bending, then that'll take away all of the bending action in our mesh, but we don't necessarily want to do that. Now, I find it odd. Computer's too slow for this. Do this instead. Go over here. Let me zoom in a window instead. Control W, show the analysis model, shrink objects. Oops, I need to uncheck that. There we go. So I'm not sure why this is happening, but it's giving me 2 elements per bay in some cases, and then over here it's giving me 3 elements per bay. And I'm not sure why it decided it needed 3 elements there. That's part of the the quirks you get out of the automatic meshing. Maybe it decided that the distance between this floor beam and that floor beam was just a little bit too far. Maybe it was 8.001 feet. So when it said I need at least an element no bigger than 4 feet, maybe that triggered some kind of a, that's odd. I think it did the same thing up here as well. Yeah, and here it adjusted the length as well, which is strange. I'm at a loss as to explain that. And that's part of the automatic meshing thing that's rather enigmatic. What I am going to do though is one more thing here. I'm going to go in and select that area object. I've got to make sure it's in the view over here before I can actually select it. Hit apply. Now I can select that area object. And if I want to, what I can do then is copy that. And so I can replicate that, or I can copy it. Hit Control R, but I guess it didn't take. So let me go here to edit. There we go. I guess I didn't have that selected. There we go to replicate. I can replicate it in the Z direction at 12.5-foot increments. And I think it's 7 copies of it that I want. Hit apply. Hit close. I can go over here and set a 3D view. And now you can see I have that floor slab modeled everywhere. Now I probably want a different slab at the roof level. It's not common that you would have a 6-inch concrete slab defined for the roof unless you're designing it for future expansion or something like that. But I won't take the time to define that right now. Okay, so there's one other option that I wanted to define. Let me undo that. I'll take away those copies. Let me go in here and I'm going to change the load that I had. So I had an area load, uniform shell loading. I'm going to delete that. So I'm going to delete existing loads, hit apply. That load is now gone. I'm going to go in and I'm going to assign an area load, but I'm going to use the uniform to frame loading instead. And let me go with dead load again. We'll go 65 pounds per square foot again. And I'm using one-way load distribution and 65 kips per foot. So go like that, hit OK. Let me run it now. Okay, notice that I did not get that error. Okay, never mind, I did get the error. Let's go in and look at the mending moment diagrams that come away from that. Yeah, that was worth a laugh. I'm glad you guys were paying attention. Book too soon. Okay, now let me go in and look at that beam. I'm going to have to zoom in on it. Come on. There we go, finally. There, now you end up with, I think it's a different beam, that's why I'm getting a different moment. But what it's doing is it's using that uniform to frame. It actually takes the load that was specified for the shell elements, and it uses a tributary width or a tributary area approach, and it basically takes the load that would be applied to the shells and it puts it directly on the frame elements that are supporting the shells instead of putting it on the shell elements themselves. And so if we want to now, this is another thing I didn't rehearse beforehand, we can actually go in and define 0 thicknesses for the area objects. and rely on our joint constraints instead. There we go. And so I can go in now and define, say, for that area object, let's see, assign area property modifiers. There it is, area stiffness modifiers. So I can go in and set all of these equal to 0, and it basically takes away the bending stiffness that I have associated with those shell elements. Close that, close that. Now if I go in and run this again, we'll see if it changes the shape of the bending moment diagram that I was looking at for that beam. Yeah, now I'm getting more errors. Okay, let's take away the shells. And now we're getting a different bending moment because the shells aren't participating in the resistance of the load. All right, so that's enough for now. You guys, this is beyond what you need for homework number 7. Homework number 8 is a matrix analysis. So this is going into what you would need for homework number 9. That hasn't even been formally assigned yet. So we'll go ahead and break off of this for right now. And what I'll do for the last few minutes is launch eTabs instead. I better close SAP or that's going to lead to all kinds of resource issues on this computer. Now, I know Maggie did a little bit of an intro, so this might be a bit redundant with what she did, but I'll go ahead and start from scratch anyways. And start doing a model of the Tower of Terror in eTabs. Okay, and one of the things that eTabs is really good at is modeling buildings that have vertical regularity. So if every floor is the same in a structure, that's where eTabs really shines. So, I'm going to generate a new model. I'm going to use the built-in templates that are available. I'll use AISC 15 as my steel selection database. This particular version of eTabs is a little bit older, so we don't have the option of using ASCE 722, but we've been using ASCE 16 anyways. So there's the 16 edition of the AISC spec, the 14 edition of ACI 318. Go ahead and click there. So I'm going to use a steel deck. Model. There we go. And so I can define the overhangs that I have. I'm going to define it with 0 overhangs. That's not realistic, but that's consistent with the way that I'm modeling this building using this. So I have bays in the X direction, 1, 2, 3, bays in the Y direction, 1, 2, 3, and I have a 32 and a 24-foot bay width. And so secondary beams are going to be spaced at X in the X direction at 8 feet. Let that in the Y direction. They go in the X direction. Moment frames, none. Restraints at the bottom, pinned. Floor diaphragm is rigid. And so now we can put in our live loads, so 65 and 80. Right, we can define our decking if we want to. This is a bit more sophisticated. You can actually go in here and define the type of metal decking you have. So it's giving us the slab depth, the rib width, and all of that. So if you want to be specific, maybe you're using a specific version of a Volcraft decking, you can go in and define that. And it has a good preprocessor that goes through and accommodates that. I'll just leave that set as the default. We'll hit OK. Go on to the next version, the next part of it. Okay, so I'm gonna have 8 stories. Typical story height is 12 foot 5 inches. The bottom story height is often different in a building, but in our case, it's 12 foot 5 inches. I have 4 grid lines in the X direction, 4 grid lines in the Y direction. The spacing in the X direction is 32. The spacing in the Y direction is 24. And we can change our grid labels if we want to. So let's see, in the X direction, I want it to be numbers, 1, 2, 3, and 4. In the Y direction, I want it to be letters, A, B, C, and D, and I want them labeled from bottom to top. Let's see, we can put in custom story data if we want to, but we don't need to do that at this point. Let's let it chug away at this. And in just a few seconds, you can see that we have a model of the Tower of Terror, right? So what took us, 2 or 3 hours in SAP 2000 to get a half right model, we can get pretty quickly in eTabs. So if you look over here on the left, we have the Model Explorer. This gives us all the information about the project that we need. Lets us define our stories, so we have stories 1 through 8 plus the base, and then we can go through and define our frame sections and everything else that we need. So there's a few things that are missing here. For example, we don't have the braced frames in framing line 1 or framing line 4. We don't have the moment frames in framing line A or framing line D, but we can define those. If we go up here, we can go to our view and we can set an elevation view in this window. So I can set an elevation view of framing line A, for example. And then what I can do is go in and define the moment connections that would make up my moment resisting frames. And so for the where's the end releases at? It's in here someplace. Right there. So we can show the end releases that are for, and so we have basically a moment release at every end of every one of these objects. And so I could go in here, I could go into assign frame, releases partial fixity, and I can select no releases for those members. And now I have a moment resisting frame defined in that framing line. Okay, and then you could do the same thing and put in moment resisting frame and framing line D as well. We could go in and look at a view of, say, framing line 1. And now I can come in and I can draw braces. Yeah, I should have put a grid line in there. And I could make my brace frame basically that way. Better way to do it would be to put in a grid line B.5, and then you could snap to the intersection of that floor beam and that grid line, and that would be more convenient. All right, that'll do it for today. So when we come back on Thursday, we're going to shift gears a little bit. We're going to jump into some more matrix analysis stuff and carry to the next logical step. So we started with trusses, we went to beams. Now we're going to go to a combination of a truss element and a beam element, which is a frame element. And we should be able to accomplish that all in 1 hour on Thursday. So I'll hang around for a few minutes now if you guys have any questions about something specific, but otherwise I have office hours tomorrow at 1 o'clock, or I'll see you guys again in class on Thursday at 12:30. All right. Thanks a lot.
When you were doing your discussion about plane elements, you mentioned specifically